So let's continue our discussion. This time, let's take it another step. And we want to be able to also solve simple trigonometric equations over the set from negative infinity to positive infinity. What does that mean? Well, that means that we're not just limiting ourselves now to values of x that would make this equation true on the interval from 0 to 2 pi, but we're saying, all right, how could we possibly express the set of all of the angles that would make this equation true? So here's sine of 2 times the sine of x equals square root of 2. And we know that at this point, if we're going to solve a trigonometric equation like this, we have to isolate sine of x to one side. So we get the sine of x is equal to square root of 2 divided by 2. Well, what could we say? We know that x is equal to the inverse sine of negative square root of 2 over 2 is one possible solution. And of course, that gives us x equals pi over 4, which is our first quadrant angle at which this is going to be the right ratio, right? So we say pi over 4, quadrant 1. That works, right? But is pi over 4 the only possible angle? Well, it's not just pi over 4. Although pi over 4 is our first quadrant angle that makes it true, we could also say that the sine of any other angle that's coterminal with pi over 4 makes this equation true. So we could also say any other angle that terminates in the first quadrant that's coterminal to pi over 4 would make it true. For example, adding 2 pi to pi over 4 gives us 9 pi over 4. As does adding 2 pi again, which is going to give us 17 pi over 4. By the way, if you're wondering what I'm doing, all I'm doing is I'm adding multiples of pi, 2 pi, right? So say pi over 4 plus 2 pi. And 2 pi itself is 8 pi over 4, so that gives us 9 pi over 4. Then we'd say 9 pi over 4 plus 2 pi. That gives us our next angle of 17 pi over 4, and so on. What's happening right here? Well, it's not just pi over 4. It's actually pi over 4 plus any multiple of 2 pi, right? Any whole number multiple of 2 pi added to pi over 4 is going to give us an angle whose sine would be square root of 2 over 2. So the way that we normally state that is say pi over 2 plus 2 pi times n. And again, I guess we should specify right here that n is an integer. Right? Because x equals pi over 4 plus any whole number integer multiple of 2 pi, we're going to get a value. So that is one solution. How about in the second quadrant? Well, we do the same trick that we did before. That is, we're going to use pi over 4 as our reference angle, except we're going to use that in the second quadrant. So that means that our second quadrant angle, pi minus pi over 4, is going to give us the angle 3 pi over 4. So that is another possible solution, that x could equal 3 pi over 4. But as before, since we're not limiting ourselves to an interval over which we only look at 0 to 2 pi, what else could we say? Well, it's not just 3 pi over 4, but any 3 pi over 4 added to any multiple of 2 pi added to the basic angle gives us a coterminal position, right? So we could say 3 pi over 4 plus 2 pi would give us another such angle, right? That's 8 pi over 4 plus 3 pi, that's 11 pi over 4. So the sine of 11 pi over 4 would be square root of 2 over 2, and so on. So what does that mean? Our answer right here is going to be 3 pi over 4, the basic angle on our interval from 0 to 2 pi, added to 2 pi n. And that's in fact how we're going to state our solution set. It'll be the set of values such that we can take pi over 4 and add any whole number multiple of 2 pi n, and 3 pi over 4 plus any whole number multiple of 2 pi, which we write as 2 pi n, as long as we recognize that n is an integer. And so we're done with this problem. More to come.